And then it just cut off at 13 minutes.
See, the universe didn't want anyone to know that I can't spell. All right, guys.
What got you yelling at me?
Every day?
What got you yelling at Charlie?
Oh, yeah,
Great.
I remember that one.
Love it. I'm so proud.
Yonder kept showing me that one.
Okay. Shh. Okay. If you remember in grades 9, 10, and 11, we learned about the octet rule. Right? And what's the octet rule state? It told us that atoms must have 8 electrons in their valence shell, right? And that was kind of our default. Whenever we drew Lewis diagrams, we were either trying to get an empty outer shell or we were trying to fill it up to 8. And if you look at the periodic table, that makes sense because that combination of 8 represents the s orbital and the p orbital being full. Does that make sense? And when we draw Lewis diagrams, we actually tend to sort of, for anything like in the p block down below, we actually tend to just ignore the d block altogether of their electrons. Does that make sense? We kind of ignore the d orbital because it's clumsy to draw 18 little dots in a Lewis diagram. So even if you're drawing a Lewis diagram for bromine or iodine, we actually usually just drew it as octet, right? We draw bromine and iodine as having 7 electrons and needing 1 more, even though bromine doesn't have 7 electrons in its outer shell. It has 17, right? And that's because we find that chemistry, especially when we're talking about covalent compounds and covalent bonding, tends to work with just those s and p orbitals. Does that make sense? So we focus on that. Yeah. So for example, if we look at magnesium, what's magnesium's valence? Well, we could say magnesium's electron configuration down here, but what's its valence? How many electrons does it have in its outer shell? 2. And what's its Lewis structure? How would we draw a Lewis diagram of magnesium? Do we remember how we do those?
With the brackets in the name.
Brackets.
Those thingies.
When do we use brackets in a Lewis diagram? We do use them sometimes.
Ionic compound.
For ions. And here we're not talking about the magnesium ion, though you're totally right. If we were drawing the magnesium ion, we would. But here we're drawing magnesium in its elemental form. So we'd use the symbol Mg, and we want a couple dots. And by convention, we go, up, down, left, right. It doesn't actually matter where you put them. Don't put them together, because as we now know, who tells us that they won't pair up before every position gets 1? Hund's rule, right? What would the energy level diagram of this be? Well, for magnesium, it has a full 1s orbital. Keep me going. Is it full?
Yes. And then
Okay. Then? Okay, how many? And it's full?
Yeah.
Okay, next?
And then 3s is full.
Is full. Okay. So actually these should be paired together. Interesting. And that's okay. How would we write this electron configuration? And we could say 1s2, 2s2, 2p6, 3s2. That's totally fine. How else could we write it?
3s.
Yep, but what would we have to put in front of it? Neon. Good. So electronically speaking, talking about its electrons, this is like a neon atom, but in addition to that, it has 2 electrons in its 3s orbital. Good. All right. Take 35 seconds, do the same for these guys, for nitrogen and for sulfur. Did you just write S for nitrogen?
That's a 5. Sorry.
Oh, no, that's fine. That makes sense. No, I'm not.
I put sodium for this.
I know, I saw. That's why I was looking at it being like, poor Caitlin is having like an Orlando moment. My goodness,
Leave me alone. Where's nitrogen? Oh, there it is. Oh my god, I keep reading 3 P's. We're both straight gonna go. I can't do this. I'm trying to look at the number, the top number. Yes. We're so smart.
Yes. Ni is nitrogen or nickel?
I'm not telling you that.
Figure it out.
You could tell her. Just 'cause I'm not doesn't mean you have to be difficult.
So, nitrogen's N? It's
Yes.
N is nitrogen, Ni is nickel.
Okay, thank you. Sorry, my brain stopped working.
be sorry. Holy moly, don't do that.
5.
What? Really? That's fun.
Let's wait. 1, 2, 3, 4. It's 3p next, right? Am I tripping out? Losing shit.
So would it be helium for nitrogen? Is it helium?
Yeah. Yeah, it's 3 to 3.
And then how do you do the bottom thing?
It's just this.
How do you
Like, you know how you have,
Okay,
you have how
nitrogen, what's its valence?
you have the long form?
5, which means, of course, it has how many electrons in its outer shell? 5. So how would we draw a Lewis structure for that?
I remember.
Yeah, that's right. And where you put 2 is up to you. I'll put 2 there. That's fine. Doesn't really matter. What's its energy level diagram?
1s2.
Yeah, it has 2 electrons and 1 s. Then next, 2s. It's got 2 electrons. After that,
And then 2p, and then there's like 1.
Oh, wait, I forgot.
1, 1, and 1. Cool.
This is bullying.
Good. How's that? How would we write its electron configuration?
Helium.
It's like helium, and on top of that it has...
2s2, 2p.
Very good. Okay. What about sulfur?
6.
Okay. S?
2, 2, 1, 1.
Yeah, and where you put the 2s doesn't matter. Usually when we draw Lewis diagrams, we're going to put them where it makes sense based on what else we're drawing, right? Cool. What's its energy level configuration? 1s2, 2s2, 2p, 1, 2, 3. So there's 6 there. And 3s2. And then 3p. And how many have to go in 3p? 4. So should that look like this? Yeah, because if we actually fill them in, it would go like this, right? Everyone gets 1, and then this one gets its second. Whose rule is that? Hund's rule. Good. Okay. And how would we write that electron configuration? Neon. Very good. Okay. How's that feel? That's not really anything new. Just making sure that we can kind of relate counting how many electrons in the outer shell, draw a Lewis diagram, drawing the actual energy level diagram, writing the electron configuration. That feels okay?
Yes, sir.
If it doesn't, you tell me.
No.
All right, cool. Then let's get talking about what happens when we have things meet up with each other. So the first nice easy one is ionic bonding, right? And if you remember, we said that if there's a big difference in electronegativity, what's electronegativity again? In a while, maybe since you've used that word.
No. Yeah.
Not the charge.
No. How much energy it takes to pull away or gain.
That's different. That's ionization energy or electron affinity, but it's related.
Of the amount of energy it takes to take an electron.
Again, really close. That's ionization energy, but it's very much related to that. Yeah.
Tendency of an element to react and
Yeah, and specifically in which direction? It's not you're completely right. That's the tendency to react, but reacting can go 2 ways. It can be giving away electrons or taking them. When we talk electronegativity, if you're more electronegative, are you more likely to take or more likely to give? Take. It's the tendency.
Negative.
Oh boy. ENCY? That looks so wrong to me, but I'm going to trust you. We're going to move on. It's the tendency of an atom to gain electrons. So if there's a big difference in electronegativity, like there always is between, what is kind of the dividing line between things that like to give away electrons and things that like to take them? Yeah?
No, I was thinking, that's not a hand up.
I mean, it is, but what you mean is it's not like an attempt to answer. Which,
yes.
Yeah.
The amount of electrons in the valence shell.
Yep, that's totally true, absolutely. And in general, what do we say? Sorry? Sure, I don't know what that means, but cool. Because you fancy McGee using words, cat ion. I mean, you're right. I'm trying to be critical. But what's that mean? Tell me, what's that mean?
So what's the question?
Oh, sorry, I'm just going to remind myself. Right, got it.
What does that say?
Never you mind. The question was, how do we know what likes to give away electrons and what likes to take electrons? Yeah.
So element is 7.
You're the worst
electrons
teacher
have their valence shell.
ever.
They would like to take 1.
Yeah.
You're the worst teacher ever.
And
That's what it says.
One have their valence shell would like to give away.
Yeah, that was a great answer. Of course, you didn't hear it because you're busy talking. But it was a good answer. Yeah, if something has 7 electrons, it's going to want to take one more to get a full shell because it's close to having a full shell. On the other hand, if something only has 1 electron in its valence, it's going to tend to get rid of that. And the closer you are to either extreme tells you the nature of your kind of tendencies or behavior. I always think of it as it's a lot like economics, unfortunately, which is that the rich tend to get richer. If you have lots of electrons in your valence shell, you're more likely to improve that number. And the poor, unfortunately, in both economics and electrons, tend to get poorer. If you have 1 or 2 electrons, you tend to lose them, right? And so, in general, that red squiggly line on this particular periodic table divides rich from poor. And just like in real life, there's a lot more poor elements than there are rich elements, right? So, if you are in sort of the stratified air of nitrogen, carbon, oxygen, fluorine, chlorine, bromine, iodine, sulfur, phosphorus, silicon to some extent, carbon to some extent, boron to some extent, but really those guys to the right, you tend to take electrons. Everything to the left tends to give them away. And what will the rich, I mean, we'll get to it next. What do the rich sometimes do with each other, but definitely not with these guys?
Share.
They'll share, but not with the poor, right? Again, sadly like economics. And what about when we get to the very far right? Helium, neon, argon, krypton, xenon, radon.
They say screw you. Keep everything.
I mean, they don't speak. But yeah, metaphorically speaking, they say, screw you, we'll keep everything. They don't even need to take or lose electrons because they are already stable, right? Different, but related. So really quickly, this should be old hat. This should take you 4 seconds. If you have taken chemistry recently and you remember it, and if it's been a long time and you forget, this might take you days. So let's just have you try for a couple of minutes and help each other out. Because again, some of you just finished a chemistry course, and some of you haven't touched this in a long time, right? But see if you can draw a Lewis diagram showing how we would form magnesium and nitrogen as a compound. And this is ionic, which means what's going to be happening with these electrons? Giving and taking. We're going to be using brackets. Yeah, cool. So again, 2 minutes. And again, if it's been a long time, don't stress. I'm not trying to shame you here. We just want to move through it fairly quickly.
Oh, we get background noise. Background music, I meant.
No, I won't do that to you, I promise. Not today. Other days I'll do that to you.
I would love to be serenaded.
Would you? That's good to know. Not everyone feels similarly, so I won't subject everyone to that.
Is this right?
I'm not looking at it. You tell me, is it right?
No.
I said you tell me. I didn't say Kaylin tell me.
I was telling her.
Yeah, the problem with that is that real? That exists. Look at nitrogen. Tell me that. Because you're on the right track. But the other trick is you try to jump right to the answer. You know what helps?
Oh, I did
Show your
look
work.
at the charges.
Yeah, show your work. Show your work. I'll give you another map. What indeed? Look at Paige, not me. How we doing? Good. All right, talk to me, team. What's happening here?
Science.
Okay, listen, if you don't have a constructive answer, you don't have to answer. One of the options is just nothing. So yeah, talk to me. What's happening here? We want to show a bond between magnesium and nitrogen. So listen, what we're going to get in the habit of whenever we do anything like this is start by just drawing these things. So how do I draw magnesium? Yeah, Charlie. Yeah, a Lewis diagram. Cool, 2 electrons. Okay, and then what about nitrogen? Sure, why not? Okay, 1, 2, 3, 4, 5. All right, and this should be, pretty obvious. Which one of these is going to be, first of all, are they going to share? They can't share, because can magnesium share its way to 8? No, not possible. So they're going to give and take. Which one's going to give? Okay, so magnesium starts giving away. So it gives away an electron. Great. Gives away another electron. Magnesium now has an empty shell, which really means it has a full valence. Because look at magnesium. What's magnesium's shorthand notation again? Yeah, magnesium is like neon, only it's got these 2s electrons, right? So once magnesium gets rid of those 2 electrons, it's just like neon. It's basically a noble gas, right? It is stable. Now the only thing is, to become stable, it had to get rid of 2 electrons, so what's now true about it? Yeah, it's got charge. Its charge is going to be positive, because you get rid of negative things, you become more positive. And how many negative things did it get rid of? 2. Can I draw neon here and say, great, now here's neon, and it's got 1, 2, 3, 4, 5, 6, 7 electrons, negative 2. Does that work? No, the problem is it's not stable yet, right? Did I say neon? I meant nitrogen. Let's carry on. So what does nitrogen need, unfortunately? Yeah, it needs another magnesium, because what does it need another? It needs another electron. So no problem. Now we have this magnesium. It gives that electron away. And now we have nitrogen here. How many electrons does nitrogen have now? 8. And to become this stable octet version of nitrogen, it had to get how many electrons? How do I indicate that? Awesome. Okay, we're done? Yeah, we got this unhappy little magnesium here. What do I need? Another nitrogen. How many electrons will it start with? 1, 2, 3, 4, and 5. And of course, magnesium can give that electron away. Why I chose that particular path, I don't know. There we are. Okay, and that magnesium is now happy, right? It's got an empty shell, and again, how did it get there? +2. But is nitrogen happy? What do we need? We need another magnesium. All right. And now, finally, we get a situation where the numbers work, right? And so what we end up with is another full nitrogen. It will be what charge? And we get another empty magnesium, and it will have a charge of +2. What is the formula of this compound? Mg3 and 2. Very good. What's that called? Magnesium nitride. If I want to know its molecular weight, what could I do? Or its formula weight? What would I do? What would I do? Talk to me. Okay, how many magnesiums do I have? So what do I have to do? And what is the molecular weight of magnesium? Is it 24? I'm going to just say 3. And what's the unit on that? It could be U for atomic mass units, but what do we tend to work in, being more sophisticated chemists than that? Grams per. Great, and then what would I have to add to that? Is it 0.01? Yeah, so 14.01. Yeah. And then, if we wanted to, we could grab a calculator and do that. 3 times 24 is, I don't know. That's 72, and then one more is 73, plus 28. So we should be talking 101, I think. Is that right? Somebody do that math for me, will you? Sorry? Yeah, is it 100.9 something? 100.92. Cool. There we go. All right. Just wanted to make sure we remembered that. It's not really the point of today's lesson, but we don't want to forget those old skills, right? Cool. Okay, so ionic compounds are easy to work with, right? Then we get to covalent bonding. And covalent bonding is where we have less difference in electronegativity. In other words, it's where the rich meet up with the rich. So specifically, if chlorine meets up with chlorine, nobody can fight the other for the electron. They're equally strong, right? They're both chlorine. So if I go to draw chlorine, how do I draw a Lewis structure of that? Yeah. How many electrons? Yeah, 1, 2, 3, 4, 5, 6, and 7. And the other chlorine, of course, would have 1, 2, 3, 4, 5, 6, 7. I cheated because I knew where they'd go, but I should draw one in each place first. And these aren't going to give and take electrons. They're going to do what? Share. How do we typically show the shared electrons? This is clumsy. Just a line. And if I'm drawing a proper Lewis diagram, I still draw every free electron. We tend to get lazy and just work with what we call structural diagrams, where we don't draw the free electrons, or what we call the unshared pair of electrons. But if you're drawing a Lewis structure, you actually have to draw both unshared pairs of electrons. Oh, fun fact about shared, not spelled with an I. I was thinking ahead to pairs. My life is a lie. Versus the bonding pair. We're going to draw tomorrow. Well, not tomorrow. I'm gone tomorrow. Tomorrow you're going to do a little assignment. But we're going to draw on Friday what this looks like at the orbital level. We're going to see how do these orbitals actually work with that. What does it really mean for for an element, for an electron to orbit two atoms, right? Something's going to have to happen, right? Because that's obviously a very different orbital shape than orbiting one atom. But by the way, plenty of solar systems out in the galaxy around us are what we call binary. They have two stars at the middle of the solar system. I will not.
This is Mrs. Middleton, and I have an announcement for any of the art students who are in grade 9-10 in Mrs. Daly's Semester 1 art class. If you had artwork displayed on the bulletin board across from the art room, please come to the art room today at the beginning of lunch for some information about your artwork. Thank you, and again, sorry for the interruption.
By for some information, is that going to be like, your art sucked? Just so you know, this painting was terrible. Yours is pretty good. I'm so glad I'm recording this right now. Please don't play that for Miss Middleton. But I just picture her being like, all right, I just wanted to tell you that this is trash and I never would have hung it up. Carry on. Anyway, that's inappropriate. I'm sorry. So for simple covalent bonding, we can pretty intuitively work out how they bond. Does that make sense? What about when they're not intuitive? Now, carbon dioxide actually is pretty intuitive because if we wanted to draw it just this way, don't do this. We'll just do it here. Carbon dioxide, you can probably figure out. What is it? It's a carbon and it's two oxygens. And you just instinctively know, how many bonds does carbon want to make? 4. As a rule, it wants to make 4. How many does oxygen want to make? 2. And so we can pretty intuitively figure out what this is going to look like, right? Which is double line here, double line there. And of course, if this is 4 pairs of electrons, does carbon have any electrons in its outer shell that aren't involved in making a bond? No, but what about oxygen?
It's still got 2 bonded pairs each.
Yeah, it's got 2 bonded pairs, and so that means it has to have 2 what we call lone pairs or unshared pairs of electrons. So you could just kind of work that out. But that is only possible because we kind of have a sense of how this gets put together, right? The other thing is it works because it follows all the basic rules we taught you in grade 10 and 11, which is carbon wants to make 4 bonds, oxygen wants to make 2 bonds, and that's the holy word and nothing ever changes. But of course, if there's one thing you'll learn in science, it's that at every time you move up to a higher grade, the first thing we tell you is all the ways we've lied to you. Not everything's going to work out as nicely as that. So I want to teach you how to do this with an easy one, so when we get to tricky ones, we can kind of work it out. Does that make sense? Okay, So the first thing we want to do is, with carbon dioxide, we want to count the number of electrons we have to work with. And when I say electrons, I mean valence. All right? Because again, where does chemistry happen? In the valence shell. All right? We're not getting any, if you were talking about carbon, its 1s electrons are not involved in this. All right? They are safely tucked away, held nice and neatly close to the nucleus in shell number 1. Does that make sense? On the other hand, its 2s electrons are in its valence shell, so they will be available to do bonding, as will its 2p electrons. So each carbon gives us how many electrons to work with? 4. Okay, and then we have 2 oxygens, and each oxygen gives us how many? Yeah, that's right. Sorry, see, you said it and I wrote it, but no, it's 6, right? So we have 4 from the carbon, and oxygen has 1, 2, 3, 4, 5, 6. You can tell me to write anything I'd write. You could be like, Orlando's stupid, and I'm just not even going to think. I'm just going to write it right on the page. How many electrons is that total? 4, and then 6 would be 10, and then 6 more, because we have 2 oxygens, would be? Nope. You got it. So that no sounded negative. No, 16's right. Good. And actually, maybe a better way to write it would be this. Just don't change a thing. But, well, you know, if you just want to, if you want to make a little table, you could say, like, you know, we have one carbon, and that is, in each carbon we get 4 electrons. So we have a total of 4, right? And then we have 2 oxygens. Each oxygen has how many? 6, which gives us 2 times 6 is 12. And so now if we do total, we have a total of 16. However you want to do it, that's fine. But does that make sense? I'm not going to lie, I would never actually write that out like that because I'm lazy. But does kind of the thinking make sense? Almost like a little invoice. We have 1 carbon at 4, so that gives us 4. We have 2 oxygens at 6, which gives us a total of 12. That gives us 16. If this thing had a charge, we might have to think about this. If this had a -2 charge, that would actually mean that we had some extra electrons. If it was -2, how many extra electrons would we have? 2. We'd have to change this number. If it was positively charged, this number would have to be lower, right? Because it would mean this thing had lost electrons. But here, the total is just 16. Does that make sense? So now, what we usually do is we arrange the atoms so that the middle atom is the least electronegative. And as a rule, if you look at the periodic table, we said the rich atoms on the right want electrons more, and the poor atoms on the left want them less. You can look up the number if you want, but just visually, which of these wants electrons more, carbon or oxygen? Oxygen. So which one wants it less? Carbon. So we're going to put that in the middle, and we're going to put the other ones around it. And as a good rule of thumb, that tends to be how these things work. So now, and by the way, here I'm going to show it step by step. In the future, you would just draw it and start modifying it right in place. But here we're going to kind of show it in boxes to show you kind of the steps you'd follow. So when you go back and look, you can see the steps you'd follow. You're never going to draw this 6 times in a row again. I mean, maybe you will, but I wouldn't. But we'll do that a couple times in this lesson to help us get a feel for it. Does that make sense? So now we would already have that drawing. And what we would do is we'd say, okay, there's going to have to be a bond between the middle atom and the atoms it's connected to. At least one. Could be double, could be triple, but we know there's going to be at least one. So we're going to start by assuming we have one bond to work with. Does that make sense? Then we're going to go back here and we're going to complete the octets of everything but the middle atom, by which we mean we're going to add lone pairs until they get up to 8, which means this is going to need 3 lone pairs, and that's going to need 3 lone pairs. Does that make sense? So if that was making a single bond, how many more electrons would this need? 1, 2, 3, 4, 5, 6. And this one would need 1, 2, 3, 4, 5, 6.
Would carbon need 4?
It would, but what we're going to do is we're going to start with the surrounding atoms. Again, I'm teaching you a method to follow. So when we get to things that have weird, tricky structures, you'll be able to figure it out. So these are steps we want to follow. Now, we happen to know. Does carbon dioxide actually have 2 single bonds here?
No.
No, but pretend we didn't know that. We follow these steps and it'll help us get there. Does that make sense? You just gotta trust me. So now, is this finished? Obviously not, because oxygen has 8 electrons, oxygen has 8 electrons, but carbon only has 1, 2, 3, 4. It's not correct, but that's okay. We're not done yet, right? So when we're done, it's got to be right. It doesn't need to be right yet. So now, what you want to do is you're going to count to make sure you have the right number of electrons. All right? So we're going to take that drawing we just, that's in the middle. We're going to take the drawing we have, and we're just going to count the electrons. And remember, what number are we trying to get? 16. Now, if we need more, Kate, you just told me, where would they go? They'd go on carbon. But if you don't need more, then we can't put more, right? So let's count. How many electrons do we have? 2, 4, 6, 8, 10. Because remember, what's a line represent? A pair of electrons that are shared, right? So that's 2 electrons. 2 electrons here. 12, 14, 16. So in this case, I have the right number of electrons. That won't always be true. In this case, it is. What that means is, don't add any to carbon. In other words, if this had 20 electrons, we would put 4 more on carbon and then we'd be done. Does that make sense? But in this case, it only has 16 electrons, so it can't give any to carbon. Which means, does this structure work? It's not very stable because carbon only has how many electrons right now? 4, right? And that's not going to be stable. So now in the last step, what we do is any more bonds that carbon needs to make, it's going to make by we're going to say this actually isn't a lone pair. These electrons must actually be shared with carbon. Does that make sense? Mm-hmm. So we turn unshared pairs into shared pairs until everything's making enough bonds. Does that make sense? So now we'd redraw this. But when we redraw it, what we would say is, okay, this pair of electrons, we're going to actually turn into a double bond. And then we could do the same with this one, but we will never make a triple bond if we don't have to. We'll make 2 double bonds. Does that make sense? So we're going to say these are actually shared. And then we're going to take these and say these are actually shared. Now again, this may seem like a lot of unnecessary work to get this structure. But again, that's only because you know carbon dioxide structure and it follows our normal rules of carbon makes 4 bonds, oxygen makes 2. We're going to get to some things in a minute that don't follow those rules. So when we're done with this, carbon will now be making a double bond here and a double bond there. This will have 2 lone pairs of electrons on it. This will have 2 lone pairs of electrons on it. And that's our structure. Right, which I'm going to show that I moved the lone pairs using this green pen over here to show how they moved. Okay, now again, does that seem stupid and clumsy and like a whole lot of unnecessary work? You can be honest. People have told me worse. Just going to go look at my card again. Got it. But I'm going to show you why that's actually useful in the next example. And the next example is the nitrate ion. Now, let me ask you, the nitrate ion has what formula? NO3. How the heck is that going to work? What does this look like? How many bonds does nitrogen normally like to make?
3.
How many bonds does oxygen normally like to make? 2. Okay, without this step, try and figure this structure out for me. And the answer is you're not going to be able to get it because we're now getting to something that doesn't obey the rules. But there's a hint as to why it doesn't obey the rules. What else do we notice about the NO3 ion? Yeah, it's the NO3 ion. It has a charge, and it has a charge of -1, right? If we want to draw the 1, which you don't have to, but you can. So what does it have an extra of? It has an extra electron, and that's going to make this kind of interesting. So let's talk about it. So first of all, we're going to follow the steps we just followed, which means the first thing we're going to do is we're just going to count how many electrons we have. So let's start with the fact that we have nitrogen, and we have 1 of them, right? How many electrons does nitrogen have? 5, which gives us a total of 5 there, right? Then we have oxygen. How many of those do we have?
3.
How many does each oxygen have? Which gives us a total of 18. And then what else do we have? we have a charge of 1, right? And specifically, it's -1, which means we're going to get another electron. Altogether, how many electrons do we have to work with here? 5 plus 18 is? Plus 1 is?
Oh, no.
24. That's right. Very good. So this structure is going to have 24 valence electrons. That make sense? Yeah, he agrees. I checked. If that was impolite, I didn't mean it to be. But anyway. Okay, so how do we arrange this? Well, as a rule, what's going to serve us well is we put the least electronegative atom, rather, in the middle. What's that here? Nitrogen. And we're going to surround it with oxygens. All right. Then what do?
Single bonds?
Yeah, we would add a single bond in each spot. And again, I wouldn't actually redraw this. I would just start doing this, but we're just laying the steps out so you can see it. Then what do? So now we have this.
Put the electrons on the outside atoms.
We fill in all the octets, right? So we say, okay, 1, 2, 3, 4, 5, 6 more. 1, 2, 3, 4, 5, 6 more. Over here, 1, 2, 3, 4, 5, 6 more. Okay, then what do? What do? We count the electrons. All right, let's do it. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6.
Wait,
1,
so
2.
what happens to the 5
Well,
electrons?
hold up. The answer is as soon as these things collide, it's a big pool of electrons. And what we're figuring out now is where do they end up? Does that make sense? Mm-hmm. So let's count. How many electrons here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we have all the electrons we can get, right? So we're done? No, because the only problem is, who's unhappy here? Nitrogen's unhappy. So what do we have to form?
A fourth bond.
Yeah, a fourth bond. And the truth is, each oxygen here, because they're all the same, is equally likely to be the double bond. So the truth is, this could be a double bond, or that could be a double bond, or that could be a double bond. Since they're all equally likely, we have two options. We could draw all three structures, but they're all going to look the same, or we could just pick one. Does that make sense? I have something I'm going to tell you guys about later, but anyway, don't worry about it now. So I'm going to go with the top one, and I'm going to make it a double bond, which means how many lone pairs does this oxygen have now? Only 2 lone pairs, right? Because one of those lone pairs became a double bond. And then down here, this oxygen has how many?
6.
Yeah, 3 lone pairs for 6. Yep. And down here, 3 lone pairs for 6. All right. And then what we do is we can't forget, because we're finished now, this whole thing is only possible because what does it have? It has a charge. It has an extra electron. So we need to indicate that. That's got to be part of our Lewis structure. And the truth is, we should have drawn that at every step along the way because it's always had that extra electron. So I'm going to kind of go back and at every step along the way point out that this structure requires this to have 1 more electron than it has protons in total. Yeah. No. If you remember, what we said was we complete the octets around the surrounding atoms. Now, the truth is, you could, and then at this step, you could say if you have too many electrons, erase a lone pair, right? And then share. But just the way I teach it is it's easier so you're never erasing multiple lone pairs, is I just teach it that just leave the middle atom alone to start with. If you look up how to do this, you'll find as many different ways as there are YouTube tutorials to do it. There's not one right way or wrong way, but I always think it's easier just to teach everyone the same way so that we're all doing the same thing. Did that answer your question at all? Again, what we're trying to figure out here is how does this work? Now, you're going to note that this structure requires things to behave a little weirdly. Nitrogen is making how many bonds here?
2 or 4.
4. How many bonds does nitrogen normally make?
3.
3. That extra electron makes that possible, right? When you throw an extra electron into the mix, things can have different numbers of bonds than we expect. Likewise, one oxygen's doing what we expect it to. One of these oxygens is making 2 bonds. On the other hand, the other 2 oxygens are only making 1. And again, the extra electron makes this possible. And if you think about it, think of it this way. Look here. We threw an extra electron into the mix. And who got richer from the deal?
Nitrogen.
No, nitrogen got poorer. Nitrogen, in a normal situation, would have 2 electrons of its own and then only be making 3 shared pairs. Here, now that we gave them an extra electron, nitrogen didn't get richer, nitrogen got poorer. Now all of its electrons are shared. This oxygen is exactly as rich as he'd normally be. Then these 2 oxygens normally would have to make 2 bonds, but in fact, now they're only both making 1. So if you think about it, the extra electron basically got given to this oxygen. Nitrogen's extra electrons, where it normally would have 2, one of them just got given to this oxygen, and now it's using the other one to make a single bond instead. So by introducing an extra electron, the extra electron goes to one of the oxygens. The other oxygen takes it upon itself to steal one of nitrogen's oxygens, and now these 2 only have to make a single bond. That makes sense, because what is oxygen? It's electronegative. When situations arise that allow oxygen to get more electrons, they're going to work harder to get more electrons than nitrogen will. Does that make sense? That's why this structure is possible. We say in this case that nitrogen has a formal charge of +1, which basically means what happens is that to make this structure, nitrogen had to get a little poorer than it would normally get. We say that this oxygen has its normal formal charge of 0, and then we actually say these oxygens have a formal charge of -1. You don't have to know this for this lesson, but just notice that you give an extra electron, and who benefits from that?
Oxygen.
The more electronegative atoms. And who actually ends up the worse for it? The less electronegative atom. And that makes a structure that would be impossible. The structure doesn't work without an extra electron. Does that make sense? But when you supply an extra electron, we get this structure that seems to break our rules. But it doesn't break our rules. It just expands our rules to be a little bit more complicated than we understood them to be before. How's that feel? Not too bad? Think you guys are ready to try one on your own?
You're silly.
Oh, actually, sorry. Before we do, I forgot to mention this. We give these bonds different types of names. The first bond between any 2 things, and I'm going to redraw the nitrate ion here, like this. The first bond between anything we call a sigma bond. When we do our day on how this looks at the orbital level, we'll see how sigma bonds work. But long story short, this is a sigma bond. That is a sigma bond. And one of these is a sigma bond. Doesn't matter which one we call it. Sorry?
Is that a symbol?
Yeah, it's a letter. It's a letter of the Greek alphabet. If you want to see a proper looking sigma here, I'll get Microsoft to type one for you so you can... Well, there's one right there, but we'll make it like big. Settle down there, champ. All right, so that's a lowercase Greek sigma. By the way, if you're wondering what an uppercase Greek sigma looks like, you've seen this before. Does anyone know? No, it's not.
Oh, okay.
When do we use that in math? To mean the sum of. So lowercase sigma, uppercase sigma.
We use that for something in chemistry.
Yeah, that's right. When you add things up. When you say add all these up. Okay, so the first bond between any 2 atoms is always called a sigma bond. And then the second or third or fourth bond between things is always called a pi bond. So for example, if we went back to carbon dioxide, by the way, remind me, how many electrons, lone pairs of electrons would carbon have? What about oxygen? Yeah, 2 here and 2 there. In this case, this bond here would be a sigma bond. That bond there would be a sigma bond. But, might as well be consistent. But that would be a pi bond, and that would be a pi bond. And there's nothing magical about the top or the bottom one. Just understand that in a double bond, the 2 bonds aren't actually the same. The sigma bond is the first bond that forms between them, and the pi bond is the second one. And that's not just a random naming thing. When we get to looking at how those happen at the orbital level, you'll see that they're fundamentally different.
Got it.
Okay, questions about that? So now there's nothing to do but practice. So practice, try those out. And just listen, follow the steps we followed here, do your best with them. All right? Do your best. It's the best you can do. No, because I have to finish making it. I made it last night, and it's way too big, so I gotta pare it down. I'm not trying to like punish you guys with work. I'm trying to be reasonable. So, yep, absolutely. Just screw everyone here over by bringing. Sorry, guys. He works at volleyball. Yeah, no, I will. Yeah, but our bus comes pretty early, is my understanding.
7:30. So.
Yeah. Yeah.
Did Ellis make an announcement?
No, but I will.
Because he said he was going to, because you didn't, and now you're saying. This is
Yeah.
I'm doing yesterday's because I forgot.
Okay.
But I this is the one thing that
Sorry. Looks great. No, that looks great.
Excuse the interruption, folks. On today's cafeteria menu, we have a roasted tomato soup for $2, assorted sandwiches for $3 each, Caesar salad for $3.75, and turkey club fries for $5. Thanks for listening. Have a great day, Eagles.
Excellent. Yeah, you come to me? Sorry. Rude, I know, but I...
just mainly the nitrite one. I know I think I'm confident on my
How many electrons? Are we the right number of electrons in PPR3?
Yeah.
I think so.
I didn't like write it down,
Yep.
like it's in my head.
You should write down. I don't think I like number 2. Nitrogen has how many? We're gonna sec. Nitrogen has 5 electrons, right? Oxygen has 6.
Yeah.
So we have a total of 17 to work with, right?
Minus
1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 18 to work with. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, yeah, good. But why have a triple bond here? Because that gives nitrogen too many electrons. How many electrons should nitrogen have in its valence? No, like when you're done, everything wants 8. But right now you have this oxygen with 2, 4, 6, 8, right? This oxygen with 2, 4, 6, 8, 10, and nitrogen with 2, 4, 6, 8, 10, which is solved by, you fix both problems by, no. Yeah. So, okay, so you didn't follow your steps, right? So that's fine. So now let's follow the steps. So what we do is first, we put a double bond between, a single bond between everything, right? Like that. And then we put electrons around everything, right? Now we count. 2, 4, 6, 8, 10, 12, 14, 16. How many did we want? Which we knew, right? Because nitrogen gave us how many? 5. 3 oxygens gave us how many? 2 oxygens, sorry, gave us how many? 12. Yeah. And then the -1 gives us 1 for a total of 18, right? Which means we're missing 2, which means we put that there, right? Now we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Great. But this has 2, 4, 6, 8 electrons. Oxygen's happy. This has 2, 4, 6, 8 electrons. Oxygen's happy. But this has 2, 4, 6. So we need 2 more here. But we can't add 2 more. So we have to make... That's right. So this becomes a double bond. Okay. Does that make sense?
Yeah, I got it.
That has to be your steps. And listen, it takes a bit of practice. Like, you're doing great. But that's why it really does pay to show your work.
Look how cute it is. Okay, that's not.
Right?
It was not worth your time. How long does that take? Do you have one? I'm like, I don't know.
Well, how many electrons do you have to work with? That can't do it. Let's take a look. Sometimes 3 is 21, but phosphorus doesn't have 4 electrons. It has 1, 2, 3, 4, 5. No, it has 5. Right? Yeah, count over. It's not how many it needs, it's how many it has. Has 5 for a total of...
all the time.
Not 20, 26. So 26. So now, okay, we gotta give ourselves some space here, because I'm not saying, so here we go. Phosphorus in the middle, and then 3 bromines, right? Bromine, 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 and then we draw bonds between them, right? And then we fill in the octets. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. And now we count, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So what do we need? Nope. No. You don't add double bonds. Double bonds doesn't change your number of electrons. It just moves where they are. Right? No. So where do we put more electrons? That's right. There you go. And now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Good. And now is everything making the right have the right number? Bromine has 2, 4, 6, 8 electrons. Phosphorus has 2, 4, 6, 8 electrons. Bromine has 2, 4, 6, 8 electrons. Bromine has 2, 4, 6, 8 electrons. So that is correct. Does that make sense? Steps. Gotta do it in order. How we doing? I haven't said yet. I didn't give it to you yet. But probably Monday? Howdy.
I need this one. I already have this one.
Okay. That must exist. Where does it exist? Oh dear God, where does it exist? Why do I lose everything I touch? Is it because I'm an idiot? It might be because I'm an idiot.
I like your song.
I'm still moving.
It's a good song, right?
I'm still moving. Thank you.
I can relate.
Yeah.
So for this one, when you count them up, it's 24. So then you have to add 2 more. Would that literally just be looking like...
Yep. Yeah, but put those 2 electrons together. You know what I mean? Like they're paired. Like you're unsure. The ones on the phosphorus, don't put them on either side like that. Just put them together.
So then, in that case, when you share them...
Now you have the right number, right?
Yeah.
So then the last step is check and see if everything has 8 electrons. Right? So now, to see if we need to make a double bond, how many does bromine have? 2, 4, 6, 8.
Yeah.
Bromine has 2, 4, 6, 8.
Yeah.
Bromine has 2, 4, 6, 8. Phosphorus has 2, 4, 6,
And then if
8. We're going to put those together, but 8. So do we need to make any double bonds? No, because everything's happy.
Okay.
Does that make sense? That's it. Hey, Saidi, you got a couple of minutes? Can I take your chat? No. Don't be sorry. No sorry. I'm not sorry. I know.
thought you were gonna do the biology. I was gonna slow it down.
Wait, why? Did I just
What? What?
like
No, I just got it now. Did I do it now? I hold on for 40. I always have too much work. I play math, I play chemistry. Yeah, but I made up. I looked at the notes.
Oh, I get it now. Brody, are you coming down? What did you even say?
What?
What did you say right now?
Why did you?
That's not the one. That's
Actually, oh, you already have that.
yeah.
Hi, Sophie.
I don't know. Is there electricity? I learned this song.
Yeah, here.
It goes a little something like this.
Computer just. You just gritted away. You just gritted it away. Oh, I'm scared. Next week I'm going to dance.
You go to Boston.
Yeah, this week, next week I'm going to dance.
When are you going to Boston?
This Friday.
What dance?
You know, the dances. Those things. The one you went to before.
I don't think I ever.
You did.
If it's like at your church, if it's a school dance, and I ever wanted it, maybe I'll go.
Does Greg look like a prom guy? I don't think he would. I feel like he looks super and then he's like, I don't know. You don't look like a prom guy. Like if your girlfriend wanted to go to prom, would you go to prom today?
She would.
Lisa.
I would be.
Like would you be able to be passionate? Would you be able to be passionate about it? Like if she really wanted to, and she was passionate.
Imagine passionate from
I was just because like I owe it to my younger self. Okay.
Yes, that's true.
And my younger self was so excited. So.
I think I was super excited about prom, but I am going to go.
It was because your childhood was
Oh yeah, like
really
they don't have it once, right? So if they want to think I would get to go to the prom, yeah. No, I'm joking.
I don't know how to go to prom on this song.
You gotta wear. How about with Ellen?
If you're gonna go to prom, who would you go with?
Me right now?
It doesn't have to be like a
There's
romance.
no way you just said that. There's no way you just said that. You just said so.
You are
I would go with Sophie. I would go with Sophie. I would go with Sophie. I would bring Sophie to the prom if I were. it was okay. Like I appreciate he tried, but like he was so miserable.
Didn't he not want to dance like at all?
Yeah, he like I had to try to force him to dance. He just sat down there
Bro,
and was like, bruh.
I will dance with you all night.
I know exactly, right?
I'll be like panting like a hog, but I'll do it.
And then I danced with girls and like people, and then after a while he finally started dancing, and then while we were dancing he was like, this is so cringe, and like
Ew.
and like he wouldn't even pay for the prom. Like I had to pay for our tickets first because he just is about
What?
And like he
How much is it?
I think it was like $50, unless you were grads.
Bro.
Unless you were grads, the grads got them for free.
and
Oh.
like,
I don't know if they're doing that this
it
year.
wasn't even like a money problem thing either. It was just like I don't know.
Wow.
I think it was over.
He's not-
I think it was over $50, and then $50 if you bought it like 2 tickets.
He's not the type to take me this.
Bro, if it costs money, I will pay. I will pay for both of us. I have too many $50 bills lying around.
I don't know.
I wouldn't let
mean,
that happen.
I might just go with a friend because that's probably the most.
Did you have fun?
If they could dance.
Just don't let yourself cry. It's the one night.
See, I see no romantic future, at least in this school, as miserable as that is, so I'm fine with going with
I'm
friends.
not talking about in this school.
Yeah.
That's a lie for some reason.
Yeah. Lie for past me, not lie for me right now because.
Yeah, well, you right now is very in the past, so it kind of works.
There's a difference.
You
There's a difference, guys.
So she just has like this violent behavior that she has to do. Like you see this, she just has to do it.
know.
Mary, were you like locked in a box your whole childhood?
No, but we didn't really get out much because my dad died.
So why do you feel like you can just randomly hit people? Who didn't beat you up when you hit someone else?
Okay, nobody did. They were all just like really mean. And kind of creepy. There were a few creepy.
Those are you so funny.
This one goes the other.
I showed him.
Okay.
This song. I'm so hungry.
Get something to eat.
Now, what are you eating over there?
What am I what?
Can't eat food.
The cup, yeah.
What is it?
Noodles.
Where?
Your dad's noodles.
Alright.
Wait, everyone's allowed to grab one, right?
Yes, this is. Yeah.
Eat that.
But we don't have cups because we don't want to wash them in.
What is up, gang?
Very little. What's up with your game?
Oh, you know, this and that. Ooh, yeah. Ooh, yeah. I got new book. It doesn't really have like anything like crazy in it. It's just like a bunch of just like
Are there new guys or same guys?
it's the same guys but just like extra stuff. So like sorcerer, there's like more subclasses and stuff, and there's like just tons of subclasses, and there's also like stuff for dungeon master. This is cool. There's like a whole appendix for just like character names.
Cool.
So
The more fantasy name generator.
yeah. So there's like, you know, non-human stuff, and then it goes into like tons of humans, spanning like so many different
Yeah, like
cultures.
countries.
Yeah,
Yeah.
it's really cool. The artwork is great too. Yeah. And then I also got another book, but it's a big campaign. So I didn't bring that. It's the campaign is really cool. It's called Curse of Strahd, and it's based in this place called the Shadowfell, which is like it's like the Upside Down from Stranger Things.
Yeah.
So it's like a mirror dimension of the material plane, and there's like pocket dimensions, which are like countries ruled by like evil people. And one of those countries is called Barovia, and it's ruled by this guy named Strahd, Strahd von Zarovich, and he is the very first ever vampire. And that's like what the campaign's based on. I haven't read into it, but it's really cool. I just don't know if I'll ever get time to run it because I have so much like stuff going on with
Plus with our
your
thing.
guys'
Oh my
campaign,
God.
my home campaign, right?
Yeah.
And then my one friend also has a plan on running his own campaign, so it's like this whole big thing.
How close is ours to finishing?
Probably about like halfway through, I would say. Yeah.
I'm gonna have to reel it in and like be the leader because
Yes, please. I was talking to Matt.
Yeah.
He's thinking about playing with us too, and I was like begging him to. He usually plays like neutral characters. I was like, please play like a very lawful good character who will like
we need
lead the party in a good direction.
Like I try to be, but I think I'm like chaotic good, whatever.
Yeah.
And so I have to be the enabler for Cobalt gang.
Yeah.
But also
I was hoping Pat's character would be like the good one to kind of.
he was
say,
at first. We're here to help.
Yeah, and then he just wound up.
Yeah.
But it kind of plays in against his character, or like along with his characters, because kobolds are very stupid. You know, they're not very smart. So
They were featured in a game I just saw.
Yeah. Oh, yeah?
It's called Home Safety Hotline. I didn't really you work as like a phone operator, but the calls they range from like termites and bed bugs to like fantasy stuff, and it just gets more like I think of like fae stuff.
Oh, that's cool.
And right at the end, like you get the final like options you can choose, and it's like warlock, remnant, kobold.
That's cool.
And like skinwalker stuff. It's cool.
That's sick.
It's freaky.
Yeah, we'll probably start up again next week.
Yeah.
And then, yeah, we'll see if I think Matt is gonna join us.
That's cool.
I just don't know who he's gonna play yet. He's thinking about playing maybe a paladin, which would be good because they're like divine, warriors of like a pantheon or like a god.
Yeah.
And they're all about like.
We need some divine intervention.
Yes. Very much so.
Severely.
Yeah. It'll be exciting to see what happens.
Yeah.
We've gotten some new minis and stuff as well, so it's fun to use those. Yeah. It's crazy how long you guys spent just absolutely terrorizing. Yeah. Because every session, I was like, okay, we're gonna get some progress today. We have to. And then at the end of the session, I'm like, that went absolutely nowhere.
Now that I know this, I'm gonna, I'll just,
Like, I'm trying not to railroad you guys, but I'm also trying to get you to follow the plot lines.
I don't want this to turn into like fail RP.
Like, I love that you guys are really big on roleplay, because that's something I don't really get a lot out of my home campaign.
Yeah.
Like they roleplay, but not like as often, especially amongst themselves. They don't roleplay very much. You guys do it all the time.
Yeah. I mean, I was like role playing as like furries in like 2017.
Yeah.
I've got all the experience.
Yeah. You guys are really good at just like role playing amongst each other. We're like my home campaign. They're really good with like role playing with NPCs and stuff.
Yeah.
Just not really
Each other.
Yeah. Sometimes they are. It really depends on the situation.
Also, I feel like some people are just more shy about it. It's like, look at me doing a funny voice.
Mm-hmm.
Lend thine ear once more.
Mm-hmm. Yeah, like Matt is one of the only people who really role plays. Everyone else is just kind of like a silent, edgy character.
Yeah, I wonder if anyone would just play like a mute character just to not talk.
Daniel's character in our home campaign at the moment, he's kind of like that. He's like this 800-year-old elf, and he knows all and sees all basically. And he's really power hungry. So his whole thing in this campaign is he's kind of just going along with the characters while they're trying to stop this, life-threatening thing from happening. He's going along to try to obtain that power. So yeah, that's kind of exciting. But he's like playing along that he's trying to help. He's trying to,
Do they know this?
Somewhat. Like he hasn't told them his exact reasons for being with them, other than he's trying. He has the same goals as them, right? He hasn't like really specified why. But me and him know what he's trying to do. So basically, what's causing everything is this ancient obelisk, and it is broken into so many shards. And there's these evil mind flayers trying to rebuild it to turn a town into a mind flayer, right? And Daniel's character he's heard of tales of these ancient obelisks, right? He's like one of the only people who know of the existence of them. The power of them is incomprehensible, right? And he's trying to get the shards before anyone else can, and try to obtain that power. But he was too late. The shards have already been obtained, so they're just trying. Well, other characters are trying to find them to destroy them. He's trying to find them to get them for himself. So it's kind of like playing against each other, but also they don't really know. So
That's cool.
yeah.
Wait, I'm excited for the big reveal.
Yeah. And last session, they fought some ghosts in like this ancient crypt, and one of the characters, he was like this 55-year-old town master. One of the ghost's abilities is they can age you, and he got aged 30 years. So he's 85 years old in our campaign now, and he's still going, he's still kicking. But
I wish that would happen to me.
Of the 4 characters in the party, 2 of them could be affected by it, because one of them is an elf and doesn't really, his age is not a big thing for him. And the other one's a ghost. And then the other 2 are humans. One of them is a young human, and the other one, which is the one that got aged, was an old human. So
Forced to become grandpa.
yeah, it kind of fits them though. Like it fits the character a bit.
Yeah.
So
Which means this isn't 13x plus 10, it's 13x
yeah.
minus 10. Which means you didn't subtract 10 from this side, you...
Our campaign is, I think, the biggest group of players I've DM'd for. Yeah. Because I'm usually used to doing like about 4, which is what we had at the start. 3. And then Pat Daniel came in, that was 5. And that was about the same as I've DM'd for before. But now with Matt coming in, that'll be 6. That'll be the biggest. But I've always wanted to DM for a huge group of players, just to like get that experience.
Those ones probably like I've probably been like ones with like 20 people.
Oh yeah.
They probably take so long, but it's probably fun.
Mm-hmm. Yeah, one of the problems with DMing for so many people is it can get like boring for some of the other players, and it's hard to pace.
Yeah.
Also, with so many characters, there's so many backstories and so many plot lines you have to go along with, and it can be a lot for the DM to make everything kind of circle around for everyone.
Yeah.
But that's the fun part.
That's That's why my character, I didn't even give a backstory aside from whatever is on the sheet.
Yeah.
I think just did something once.
Yeah. Yeah, your character's whole like thing is that they went to the town to sell some gold frogs. And
that's my whole goal in life.
And now you're just like going along with this ragtag group of adventurers to
I don't give a shit. I just wanna do
just having some fun. And the rest of them are just wanting money.
Yeah, you don't even like know.
Oh, it doesn't ask us to solve the linear system.
Yes.
It just asks you to get this far.
that Corvin guy.
Yeah, read the question. In each pair, decide which equation will use to solve variable. Do that step.
Yeah, but
solve the
even
linear
if
system.
we're
This one actually asks
oh my god.
I saw this really cool subclass for Druid in here. And
Druids are like the trees, right?
yeah, they're like Quinn's character is half Druid, half Rogue. It's called Circle of Dreams. It's really cool. Basically, you're like connected to some sort of fey creature, and you believe in like your powers of like dreams and stuff. And one of their abilities, this one here, whenever like you and your party short rest or long rest, you create like this 30-foot invisible dome, and all of you like in that dome have like advantage on stealth checks and perception checks, and also any flame doesn't exist. If you're like looking into the dome, you can't see it. So like you're like it's hard to even track you know.
That's cool.
Which is I think a pretty cool thing to like shield you from enemies if you're like camping out in the woods or something. So I really want to play a druid one day. I think it would be very interesting.
Yeah, do you ever like play?
I played twice. My first character I only got to play for about 4 sessions. He was a hippopotamus cleric. He was really cool. And then my character that I really got to play, who I loved dearly, his name was Owlbear, and I think I told you about him a little bit maybe. He is a human gunslinger fighter, and he's a cowboy, right? And his whole thing is that he killed an owlbear when he was really young, and the fur of the owlbear he turned into this big coat, and he only wears that coat, and that's what he gained his name from. So no one really knows his real name. And he was kind of like a bounty hunter, but also like an outlaw. And he went to this island with some other people, and try to like save the people there because he's still a good-hearted person. Tries to help, and he went on this whole like adventure with these other 2 people. And at the end, they ended up going to the Shadowfell, which I was telling you about, and because that was connected to the other one of the characters' backstories, and he ended up dying at the very end. And
I hope my character dies, but not soon. Just towards like the end, that would be very funny.
Yeah.
If I die, not even from like a cool battle, I just like have like 1 health point left, and I fall in like a little this
spike.
Hole.
Yep. It's hard to die. But when it does happen, it's a big moment. In our whole home campaign, we've had 2 deaths. One of them was reversible. The other one, which was my character, was the first true death we ever had, and that was the first time I got to actually play a real character. It was sad.
I think the funniest thing that could have happened for us was Pat and Daniel's character.
Because that was like another one of the first times I've really ever done death in D&D.
Yeah.
And at low levels it sucks, right? Because it is common at low levels.
Didn't Caden's character die in like the first round?
He got knocked unconscious. But
I'm always carrying these people's like dead bodies around.
yeah.
Oh yeah. Perfectly normal thing to say.
In D&D.
Yeah, okay.
And every weekend.
And on Tuesdays. Dead Body Tuesdays. Yes, normal. You heard me. Get for eavesdropping. You wish.
Because, well, I worked last night on a Tuesday, and of course, more teenagers come in. The same group always, and they're from my old school, and I want to like beat them up, but I can't because I'm not mean, and also I don't really care enough to. They were getting like kicked out, and I'm assuming they were gonna get like fully banned this time because my coworker, she pulls them all up to the front of the counter. She's like, "Everyone, write your name." And I had like turned around. They were giving some of their names, and then I turned around, and then I'm like hearing laughter, and I turned. They all ran out. So they'll just come back. This happens every time I'm there. Is a group of kids come in, and they start harassing people.
Teenagers, am I right?
And it's like they're talking like there aren't like little babies and toddlers there, so they're just swearing and making like sex jokes all the time. It's like